Now there is something special about this subclass of model and this class of models. So this is, as I said, a set of models, in the sense that this is a subspace of that, not just a subset of that. To understand this, we just consider the design matrix. So the design matrix of that model, as you can easily see, is for the mu's I have got 1, 1, 1, 1, 1. For the alpha 1s, that is for the things where you have got variety 1, you will put 1, 1 and 0, 0, 0, 0, 0. Then 0, 0, 1, 1, 0, 0. This is for alpha 2, and 4 zeros followed by 2 1s. That's for alpha 3. So that was the design matrix. Now think of what is going to be the design matrix in this case. For that, the design matrix will be 1, 1, 1, 1, 1. So observe that this design matrix, the column space of the design matrix, is a subspace of the column space of this design matrix. So that is what we are going to work with. So we will be given two models. Here is my first model, the model which we believe is already a good fit. Just observe that I have added one extra assumption here. I have assumed that the epsilons are not only mean 0 and variance sigma square I, but they also happen to be jointly normal. That is the typical assumption under which we will perform our test, because we need the distribution of the test statistics, so we need a full distributional assumption, and the normal distribution assumption is the most natural one, because it makes mathematics simple, not because that is the most commonly occurring thing or anything, but that's a popular choice. So we will be given one set of model, so one model, which basically means a family of distribution, and we believe that it is a good fit. What does that mean? This means the true distribution of our data lies in or pretty close to this thing, or I might say not pretty close to, it lies actually in this family. So y will lie pretty close to column space of X, but that we are assuming that this is based on whatever goodness of fit we have done, etc. We are now happy based on domain knowledge, goodness of fit, diagnostics, etc., etc., that we are happy that this is a good fit. We are ready to give it, clinch it. Now someone gives us a restricted set of model, same thing as this, except that now we are working with some x1 instead of that x. x1 does not need to be made up of only columns chosen from columns of X. It may be just a different design matrix, of course, design matrix completely known and fixed, such that we have essentially the same type of assumptions here also, but as I have mentioned earlier, the beta here is nothing but an indexing parameter. So the beta here and the beta here are possibly different. You can see that here I said beta lies in Rp and here I said beta lies in Rq. That is, I am assuming this x is n by p, whereas this x1 is n, same n, by q. N remains the same because our observation vector, the data, remains the same. And I assume that column space of x1 is inside column space of x. That is what I say, what I mean when I say that this model is a subspace of that model, not just a subset. So it is again a linear model. So I have a column space here and a column space there. This column space lies inside that column space. One simple way of thinking is that it is possible to put restrictions on this beta such that this model reduces to that model. As in the last example, if I put the restriction that all the alpha I is equal to 0, all the alpha I is equal to 5, then the first model reduced to the second model. And that's a simple proof that the second model is indeed a subset or subspace of the first model.